Hey guys, Mr. Riz here to help you out on the 111, say it again, 411 part one. So in chapter four, we're going to look at like massive simulations going through, kind of dipping our toes into some things here. What we're going to be using is this Netlogo, and I'm going to try to use the web based version. There is a desktop based version. It works a little bit smoother. You can download it. It's free if you go to Netlogo. But right now we're going to go through this. Our goal is to basically use simulations to learn about complex systems that are difficult to observe in the real world. We're going to try to gain some insight knowledge using the iterative and interactive nature of modules and simulations. And we're going to try to derive some meaning, knowing the inclusion exclusion of certain elements is important as part of the model / simulation process. So we're going to use Netlogo. If you want to go ahead and we'll use the web-based version. You can see on this site here, you can download a desktop one or the one that runs in the browser. It's actually really nice. The browser one is pretty much, as far as I know, brand new. This was something that I think, over the past year that they've decided to implement to make people use it. The desktop one works even better than this, but this is actually really, really nice. So we'll split screen this off here. I'll have this off to the side, our instructions over here. So when we simulate in the real world, one of the benefits of the computers and their software is the ability to simulate real world systems that are just too complex or too dangerous, too expensive, too big, or too small to easily observe. So simulations allow us to learn about the world around us and solve real world problems, safely and efficiently. One of the real world systems that is too difficult but important to study is climate change. So at the end of this lesson, we're going to explore climate change simulation to identify potential patterns and correlations and to understand its bias and draw conclusions. So along the way, we're going to explore other simulations to observe random behavior, recognize the patterns, and to make predictions. So there's many types of varieties of simulator software. We're going to use Netlogo. It's a modeling and simulation software programmed at Northwestern University. It's a turtle-based system, so much like the turtles we learned in Python, but Netlogo uses a variations of the Logo language. So Logo is a good language for systems that incorporate AI or basically any emergent phenomenon. All right, so to understand the simulation, we're going to explore the simulation with forest fires. So try to think of this first question: why might simulating this be a good way to learn about forest fires? Hopefully you can think of a pretty good answer. You probably don't really want to go around and just like light forest fires to see what they do. If we can simulate those at a safe scale, yeah, there we go. So let's talk about fire here. So simulations are most useful when the real world events are impractical for experiments, i.e. They're too big or too small or too fast or too slow or too expensive or too dangerous. So forest fires can be a devastating phenomenon. Obviously, we know that it costs lives and property damage and deforestation, air pollution. We're going to use Netlogo to study the spread of the forest fires safely in confined, just within our classroom here. So we got Netlogo going on. You'll see its user interface doesn't have much of a simulation loaded yet. The empty black window is the world. So this is our world over here, in which the simulation will run. Everything will run here. We're going to explore the library that it has. So over here, if we were on the desktop, there'd be a file menu that we would use. Over here, if on the Chromebook, we're going to go ahead and look through this. Now, everything is kind of organized. We have sample models. Everything's a sample model that we're going to be using here. We're going to have to try to find fire, and that is in the earth science. So you can see we got art here, then we got biology, and then we can scroll down, then we got chemistry. So you can see it's in alphabetical order. We could look, or you can just search for fire. And you can see we got different ones. Okay, so here's sample models, earth science, fire. This is the one we're going to load up. And after we click that and open it, you'll see that there isn't much difference here. So you'll see the Netlogo user interface elements next to the world, which pops up here. Has a density slider, which we can move here, and we can have the setup and go button. So the density slider represents a variable that you can change throughout this code. The setup and go buttons initialize and run the simulation. So setup starts it up, go runs it. So you can also see that we have a percent burned variable, or not variable here. I guess it's a variable, but text box. And this is basically a read-only variable that we can't change. It's just to help us get some information. So from the slider here, record the default density is shown. So hopefully you guys can see the default density is 57 here. So if we click setup, what do you think this represents? So if you guys can look at here, basically we get green pixels or black pixels. We probably represent the green, each green pixel represents a tree. Each black pixel represents not a tree. So if we definitely change the density, I can actually type in, my number key's not working. Okay, well, I guess we gotta slide it all the way down. I can't type in. If I go down to 14, you can see we have a lot less green and more black. If we go all the way up to 99, you can see we only have a couple. So if I get to 57, so now every single time you click setup, it's not the exact same location. It's 50% of the screen is green. All right, then we're gonna click the go on this experiment. We're gonna experiment with the density slider a few times. All right, we can change the slider every single time. We have to click setup to run that again. So let's run the simulation and we're gonna observe what happens here. Okay, so there we go. So basically, what did the variations in the simulation represent in the world? So maybe we'll set that up again. You can see, so we're assuming basically a whole line over here catches fire, and it looks like it changes the color, and any adjacent tree catches fire as well. So this continues to move on a path until basically we'll keep going until it cannot go any further, until there's no more adjacent trees. And that's just the random probability of that. The more adjacent trees we have, the further this can go, but eventually we basically find a spot where it cannot connect. So this represents, the fire spreading across the forest. So the fire model lets you vary certain elements of the real world system, but not all the elements. So simulation designers must simplify simulations because the real world systems are just too complex or too practical to be fully simulated. So designers choose what to exclude and what to include according to their needs. Therefore, they introduce their bias into the simulation. So in the fire model, only the density of the forest is included in the simulation. We can observe how this one parameter relates to the outcome. So the spread of the forest fire. So with the density as the only critical parameter, what are some exclusions in the simulation that could lead to bias? So think about some other things here that we, if we could have some bias here, is there anything else that could attribute to a forest fire that we don't really know? So yeah, we have two forests that are exactly the same density, but one would have a worse forest fire than the other one. So think of other elements that could lead to a forest fire. You can talk about, how dry is the area around them. So you can have, a forest of evergreen trees up in, I don't know, in Oregon or somewhere like that, or I don't know if they're evergreens, or you can have a forest of like super bright crackling trees down in middle of California, Los Angeles County. One of them is wet, one of them is dry. If the wet forest catches on fire, even though it's just as dense as the dry forest is going to spread. So think about other things. We don't know how the wind is going to correlate. If we have a strong breeze, even though the forest is, density, more dense, that breeze could actually spread the fire further. So a lot of different things that could be going on, weather related too. All right. So the simulations can be interesting to watch and run and basically collect data. So you often want to run or rerun them quickly. So you can change the speed of the simulation in the Netlogo window. So up at the top, there is an interface and you can click the speed. Over here, you can kind of do the same here, but it really doesn't. You can click speed and drag it up here and then click go, and you can see it goes faster every single time. So this slider here and our desktop will go through. You kind of have another slider here if you use the desktop version there. So since the simulation runs a few times, you'll see the tick value. So the tick value is just basically how many steps it took. So, I mean, all these things are technically, once we have it set up, we could actually figure out exactly what the pattern is going to be. And it goes one step by step, going through each tick or each iteration to move on to the next part. So if we really slow this down, actually, that's probably too, you can see one tick, each tick goes through, you can see it's moving on to the next adjacent, green spot. to it, and it's building off of that. And each time it's building off of it. So we can increase the speed a little bit, tick, 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 let's go faster. And then if we increase this ticks, it starts to actually move when we can kind of see what's going on. All right, so what I want you guys to do here is to copy and paste this table down and to complete this here. So Control C, Control V. Basically, what I want you guys to do is to run the simulation a couple times for each one. We're going to change the density. And we want to figure out how often the fire reaches the right side of the world. Now, I would say if we split it down the middle, this over here is the right side, that's the left side. So it doesn't have to reach to the right edge, but just the right side. So I would run this a couple times for each percent. So we can go through, set it up, run this here. Now, if that's going too slow, speed it up. Okay, so I'm not sure if I would call that the right. So that's one attempt, set it up, do that again for 57%. Okay, definitely didn't do it for that one. Okay, didn't do that for that one. Okay, so one time it did. Do the fifth time. Okay, that didn't. So I'd probably say maybe 57% would be sometime. Just to show you if we change this just to 60, 3% more, set it up. See how often this reaches the right side. Okay, it reached the right edge there. We can just set it up. Oh, I guess if we just click setup, we'd leave it go high. Okay, did it that time. All right, a third time. All right, say that's three times. Yeah, 3 times in a row. Can we get 4 times in a row? Yep, 5 times in a row. And so pretty much almost always we would go through. And then after each time, maybe put an average of the percent burned. So how much was burned each time. So keep a running correlation of that. I would say probably do 5 simulations for each one of those. Go through. So who might use the simulated data for what purpose? So think about what professional would want to know this and what purpose would they be using? You can think of like park rangers or other people that are out there. Okay, so this wraps up the fire. We're going to go through these hopefully pretty quickly, and you guys have some fun with these and kind of mess around. This is a really cool software to kind of see and mess around with. You can pick different libraries too with this. All right, guys, have a great day, and I'll see you next time.